Okay, another example, and this is one where we have an electrical circuit with a resistor, a coil, and a sinusoidal input, voltage input, where we have the initial current being 0, and we want to solve for the function I of t, so the current in our circuit. So step 1, let's take the Laplace transform. The Laplace transform of L times di dt will be L times S times I minus I0, which is 0. So we can write this as L times S times I. The Laplace transform of R times I is R times I, and the Laplace transform of E times the sine of t. Well, this E we can transport in front of the L, and what we get is E over 1 plus S squared. So I've taken the Laplace transform over 3 components here, and we are left with the equation L times S times I plus R times I equals E over 1 plus S squared. So now we've taken the Laplace transform. Step 2 is isolate the Laplace transform of the variable we're interested in, which in this case is I. So we have I times Ls plus R equals E over 1 plus S squared. And we can now divide left and right by this term, and we end up with I equals E over Ls plus R times 1 plus S squared. So this was step 2. And now we'll have to rewrite this so that we can write it in terms of something we can put into our inverse Laplace transform. So we'll have to do some partial fraction expansion. I'm going to do one thing here, is I want to take factor L out of here for the simple reason that now I have this factor in the form of S plus something. So I have S plus R over L 1 plus S squared. So this is just some constant, but now I have my factors in some written in a way I can use the Laplace transform more easily. All right, so next step, partial fraction expansion. So we will write this as E over L times, well, our first partial fraction, that will be this linear term, A over S plus R over L, plus, and this will be a quadratic factor because this has complex roots, BS plus C over 1 plus S squared. Well, we can use partial fraction expansion and find these coefficients A, B, and C. We've already done that, and what I'm going to do is cheat a little, because this would take up too much of the board and it's something you can really do yourself. We find that, let's see, A in our case is L squared over L squared plus R squared. And let's see, B is equal to minus L squared over L squared plus R squared, and C is equal to RL over L squared plus R squared. And what we see is that all 3 coefficients have this 1 over L squared plus R squared factor. Well, they have the same denominator, and what we'll do is we'll take this factor 1 over L squared plus R squared in front of this bracket. So what I mean is we can write this as, oh, they also have an L. So we will write it this way. So this one is L squared. So we are left with an L over S plus R over L. And this is arithmetic, and if you don't immediately see it, just take the time to write it all out. Let's see. Now we have this B minus LS plus R over 1 plus S squared. And I'm going to rewrite this term a little more. We cancel out these L's, which is then E over L squared plus R squared. L over S plus R over L minus L times S over 1 plus S squared, because the S over 1 plus S squared is something that's in my table, plus R times 1 over 1 plus S squared, because the 1 over 1 plus S squared again is something that is in my table, and now I can see it. I can even write L times 1 here. This is in my table, this is in my table, this is in my table, and I can write this then as E over L squared plus R squared times L e to the power of minus R over LT, because this is an exponential function, minus L cosine of t plus R sine of t. So now we have quite a few steps here. So I'll recap it. We have our differential equation. We took the Laplace transform of all the three components, and we end up with the Laplace transform of our differential equation. We want to isolate I, so that's what we did in this step with some algebra, and we are left with I is E over L times 1 over this denominator, which we can separate into two factors. This is a linear factor and this is a quadratic factor. So we have a linear factor and a quadratic factor here, and we need A, B, and C. Well, by rewriting this with a common denominator, we can find A, B, and C. And what I've done is I see that A can be written as L over L squared plus R squared times L, and I can do the same for B. I'll just separate this. B is equal to L over L squared plus R squared times minus L, and C is L over L squared plus R squared times R. And so all of these coefficients have the same factor, L over L squared plus R squared, so I take that outside of the parentheses, and I am left with my L here, my minus L here, and my R here, which I fill in for A, B, and C. And then there's a little more calculation to separate this one out into a term with S over 1 plus S squared, which will yield a cosine term if we take the Laplace transform. Yes, this is the step where we do the Laplace transform, and our I of t equals this. But we have an exponential, a cosine term, and a sine term. Well, the Laplace transform of those, and if we take the inverse, we are left with these three functions. So there are some tricky bits here, especially with managing the coefficients A, B, and C, but it's no different than the exercises before, where we just take the Laplace transform, isolate our variable, rewrite it in such a way that we can take use the table and write out our solution.